What if NASA sent Perseverance to the moon? Where should I send my scientific discoveries to get them looked at? And do bright supergiant stars have habitable zones? All this and more in this week's Question Show. Welcome to the Question Show. Your questions, my answers, as always, wherever you are, across my channel. If a question pops in your brain, just write it down in the YouTube comments and I will gather them up and I will answer them here. Baby Maker. What if NASA built another Perseverance and instead of sending it to Mars, landed it on the moon, including the sample caching for astronauts to go and collect when we get there? RTGs, so you don't have to worry about the day-night cycle, and even when we go back, we can continue to do so. It's finding things to be checked out by people. Well, this is a terrific idea. Why not send a rover like Curiosity or Perseverance to the moon? And you're exactly right that one of the big challenges with sending spacecraft to the moon is that it gets really cold. During the daytime, the temperatures are incredibly high. And then the moment the sun goes down at the end of that 2-week day-night cycle, then temperatures plunge hundreds of degrees and now it's incredibly cold. And this is what knocks out most of the landers and the rovers. They're solar powered. They're able to make hay while the sun shines. They've got their solar panels out and they're able to keep themselves cool and run all their experiments and transmit data back to home. But then the moment the sun goes down, then they start to get cold. And as soon as the temperature drops too low, they're not able to maintain the internal temperature on their batteries, then the batteries die. And when the batteries die, the spacecraft is dead. Even when the sun returns, 2 weeks later, the batteries are dead. It can't refill its batteries. The solar panels are worthless. The mission is over. And so if you could send something like Perseverance or Curiosity to the moon, now you've got a rover that's equipped with a radioisotope thermoelectric generator, which is a chunk of decaying plutonium, which can then be used to keep both the rover warm and also allow it to provide enough electricity to do whatever job that it wants to do. And there are good examples of these RTGs doing this task. I mean, think about all of the New Horizons, the Voyager spacecraft. They're equipped with RTGs. They stay warm. So why not do it? Well, it's just that it hasn't been a priority. A nuclear powered, or I guess a nuclear battery powered rover would be super duper on the moon and you could get a lot of work done. Now, that said, we are having humans go back to the moon relatively soon. Although the Chinese have done sample return missions, we should be having humans doing sample return missions anytime soon now. But I think the idea is perfectly valid. There's no reason why not to. I mean, part of it is that there's a slight shortage of the RTGs now. There was like a total shortage a couple of years ago, and people had to come up with clever ideas like the Juno mission, the Europa Clipper. These use solar panels and not RTGs. They would have loved to be able to use RTGs, but they didn't have enough of them. So no reason why not. You've also got sort of the kind of terrain that you're dealing with. Like, we know that there was no long-term presence of water on the surface of the moon. And so the kinds of samples that you would be taking with your rover are going to have totally different purposes. Like, you're going to want to learn the geological history of the moon, but not as like, was there ever life there? Was there ever water there? It's just like, what's it made out of? How is it connected to what Earth is made of? And then the most interesting place that you're going to want to go is to the South Pole of the moon. And in fact, NASA is planning a mission that's going to go to the South Pole of the moon. That is the upcoming Viper mission, which is going to be going to the South Pole. It's going to be examining the regolith, trying to find out evidence of water ice mixed in with the regolith. And what's interesting is it is a solar powered rover, but their plan is for it to operate for 100 days. So it's going to go through multiple lunar cycles and still survive through this process. And it's going to have a very large battery. It's going to sort of hunker down and really try to hold on to its heat and try to make it through that lunar night. So we'll see if this strategy works. I'm sure you've noticed the Star Trek planet name that appeared above my shoulder, and this is a way for you to vote, for you to tell us what you thought was the best question, best answer, best combo, whatever entertained you. So we will post a different Star Trek planet name up above my shoulder for each one of the questions. And so watch through the whole show. And then at the end, put in the comments down below the name of the planet that you thought was the best. And we'll put in, like, in the show notes, you'll see what all the planet names are. So go ahead and do that. Now, the winning vote last week was for Jesus Solis. If satellites are the first products used for a space economy, what would be the next product? It was a fascinating question, and I'm really glad everyone enjoyed the question and the answer. Antonis Karpanos. Where should I send my scientific discovery to be checked, promoted, to be known to other scientists? Now, I'm going to assume that you're not a scientist, because a scientist will already know the answer to that, which is to publish your results in a scientific journal. The more prominent the journal, the better. If you can get your research published in Nature or in Science, then you've got a really good chance of other scientists looking through your work, examining it, and then basing their work on what your work is, double checking it, or trying to find problems in it. Now, if you're not a scientist, you're an amateur, and you have figured out some kind of discovery that you're then hoping to pass along to the scientific community, I've got bad news for you, which is you're going to have a really hard time getting any scientists to listen to you. And it's not that scientists don't want to have really cool out-of-the-box thinking, ideas that come from other sources. You know, when you've got 8 billion brains thinking about problems, people are going to come up with really clever solutions to problems. The challenge is that 99% of those ideas, 99.999% of those ideas are going to be wrong. That there are very simple reasons that anyone who has actually gone through this scientific process, who understands all of the fundamentals of how this, you know, if you're talking about what dark matter is, or where the universe came from, or how you can unite quantum mechanics and gravity, that, you know, 10,000 ideas, you will be able to rule them out as you learn the fundamentals of how the science works. And so generally, the first thing to do, if you've got an idea about some concept in physics or astronomy or whatever, the first thing that you should do is learn all of the underlying physics and astronomy to the point that you understand what is the consensus opinion of the current scientific community. And it doesn't mean that you have to go and get a PhD in astronomy. That's ridiculous. Get your hands on the textbooks that the scientists are going to be using, the physicists are going to be using. You know, there's a great textbook for, like, when I went to engineering, there's a physics for engineers textbook, and you learn a ton of physics, a ton of sort of engineering related physics. And then you're going to want to do some other, you know, calculus, and then you're going to want to do specific, like if it's quantum mechanic type stuff, you're going to want to go through and do a whole bunch of challenging problems in quantum mechanics. If it's relativity, you're going to want to go through, you know, general relativity, and you're going to want to go through the current understanding. And my guess is you'll get to a point where you're like, oh, I see where I'm wrong here, right? Like someone already thought of this in 1932, and then they did an experiment and it showed that it wasn't true. And so now they rejected that idea. Now I know why I have to reject that idea. I'm going to go back to the drawing board now with all this physics knowledge. So you're not, and so the assumption is like, that is your ante. That's like the first thing you want to do to get into the physics game, into the solving the big problems of the universe game, is to do the work to get to the point that you have the same level of just like basic knowledge as scientists. And if you go through that process and you come out the other side and you have been able to show to yourself that this idea still holds, then you're going to have a much better chance of going to a scientist and saying, look, here's my notebook, here's me going through and doing all of the equations of the engineering physics textbook, and here's all my quantum mechanics, and here's all my relativity, and I'm out the other side, and I understand, and here's how I understand what this is, and here's the math. Then a scientist will look at you and go, respect. Good, you know, that you're serious. Okay, let's take a look at what you've got to say. But then the other way to go is to find a collaborator, find a scientist who's working in this field, convince them, and then you can publish a paper together where that will then get into the hands of other scientists and they'll be able to look at it. So, you know, I would say like for anyone who's got like a big idea, you need about a year's work to go through a very compressed curriculum to bring yourself up to speed on the current consensus of the scientific knowledge in whatever is the field that you're attempting to contribute to. And when you come out the other side, if your idea is still, you can't get it out of your head, then keep going. Zeringa. I'm curious about the brightness of stars like blue supergiants. Wouldn't they be so bright that any planet within their gravitational hold couldn't possibly harbor life due to the incredible brightness? Well, theoretically, every single star has a habitable zone, because the habitable zone is just a distance from the star where liquid water can exist on the surface of a planet. Not whether or not liquid water actually exists on the surface of a planet. It's, it's just a probability. And so, for example, here in the solar system, our habitable zone extends from the orbit of Venus out to the orbit of Mars. And so both Venus, Earth, and Mars are in the habitable zone around the sun. Now, obviously, Venus is not habitable, Mars is not habitable, Earth is habitable, but you could, if you change the chemical characteristics of both of those planets, you could have a place that is habitable. So there is a habitable zone around red dwarf stars. It's really close into the star, and there's a habitable zone around blue supergiants. So before this show, I did sort of looked up one example, and that is Rigel, which is one of the most bright stars in the sky that we can see. And it is dramatically more massive and larger than the sun. And it is a blue supergiant star. And so I punched in the mass of Rigel. I punched in the radius of Rigel, because those are sort of like the two numbers that you need. And I punched in the surface temperature of Rigel. Once you have the surface temperature and you have the radius of the star, you can then calculate where the habitable zone is around that star. And I got that the inner area is 3.25 astronomical units, so 3.25 times farther than the Earth is from the sun. And the outer limit is 4.68 astronomical units, which is pretty far away. Like that's out past, it's like Jupiter-ish. And so you're going to have this big region where liquid water could exist on the surface of planets. But blue supergiants are nasty. So there's a couple of problems going for them. First thing is that they're putting out a lot of their radiation in ultraviolet. That hot temperature, they are like 12,000 Kelvin, while the sun is 5,800 Kelvin. So they are more Kelvin. And so that pushes the wavelength of the light from these blue supergiants towards the ultraviolet. And so you've got this ultraviolet radiation, and it is dangerous. Like ultraviolet radiation interacts with the atmosphere, can destroy the atmosphere, crush the ozone layer. Like there's a lot of reasons why we don't want more ultraviolet light coming from the sun. So the kind of radiation, which you sort of, talk about the incredible brightness, and yeah, the kind of radiation sort of pushes it in one realm. They can also have really nasty flares. And we saw like what happened with, say, Betelgeuse, where we had a flare. Betelgeuse can have flares that obscure the entire star from our perspective. So blue supergiants can be very volatile as well. And then the other thing is they're very short-lived. So blue supergiants, any stars that are significantly more massive than the sun, they're only going to live for 10 million years, 1 million years. They're not going to live for very long. So you've got to go and have this life set up on this planet in this incredibly hostile environment. They've got to be able to survive this ultraviolet. They've got to be able to survive all these flares. And then they've got 10 million years to get the job done, which is pretty tough. So, we will almost certainly find Earth-sized worlds in the habitable zone of blue supergiants, but chances of them being actually habitable are pretty low. But we should still look. FPL Mikkel. Is the reason for the Fermi paradox due to the Earth being unique due to its ability to support a fire? As far as I know, no other planet nor moon has the right abundance of oxygen nor the right atmospheric pressure to support a fire. And given how important controlling fire was for humans to develop skills and later on the combustion engine, can it ever be done in other environments? Yeah, so the concept that you're talking about is known as the oxygen bottleneck. And this is the fact that on Earth, we need the minimum of 18% oxygen for combustion. And without combustion, then you can't have fires. And without fires, you can't have industry. And so you can imagine that not being able to have enough oxygen in the atmosphere puts a damper on some technological civilization attempting to come up with ways to leave their planet. And that is the title of a paper by Adam Frank and some other people. I interviewed Adam Frank fairly recently, and we talked briefly about the oxygen bottleneck. And at the same time, though, if you've got an intelligent civilization, you can imagine that they come up with creative solutions to problems like this. And so maybe they come up with a chemical-based solution, or maybe they come up with a volcano-based solution to be able to solve some of these industrial processes. And you can imagine some civilization figuring out how to extract oxygen from the rocks all around them, and then use that to enrich the flame. And maybe they figured out how to make fire after all. Like if we had to crunch up rocks and pump the oxygen into furnaces to be able to make them work, we could do that. Think about rockets. Rockets carry their oxidizer with them. So the paper is great, very readable, and it's it's a very clever idea. The problem that I always have with the Fermi paradox is just like, whatever this thing is, it has to explain everything. It has to explain the reason we don't see life or intelligent life anywhere. And so even if you have any one explanation for something, as long as some other civilization isn't hampered by it, then they're going to create this ever expanding galactic federation empire that just obscures the guys without fire. So, whatever it is, whatever the Fermi paradox is, it's got to take out all civilizations. It's got to keep them all on the surface of their planets without access to technology. Gasan, do you advise me to study journalism at university? That's tricky. I didn't study journalism at university. I studied engineering, and then I studied computer science at engineering, and then became a journalist afterwards. Being a journalist isn't that hard. I mean, it just requires a lot of work and a lot of practice. And so there isn't any really specialized knowledge that a university couldn't teach you that you couldn't pick up just doing the work. So, the thing that matters in journalism and any kind of thing that requires writing is just doing a lot of work, like being able to write a lot of material. It's interesting. I use Grammarly to check my spelling and grammar mistakes. And so I get a report every week of how much I write. And I write the equivalent of a novel every month with all the writing that I do. So you don't see it because I'm just talking, but actually most of the time I spend is writing. And so I write about 25,000 words a week. I don't know, about 5,000 words a day when it all averages out. So I spend a lot of time writing a lot of words. And I have just practiced a lot. One of my writing mentors, I asked him, because he would write like 5,000 words a day. And I asked him, like, how do you do this? Like, because I would write a 300 word essay and be exhausted. And he's like, you just sit down and you just do the work. And you learn to write fast. And by learning to write fast, you put out a lot of work, and then you learn to write well. And, apart from that, like, what is journalism? Journalism is hearing somebody's story and then reporting on it and writing it in a form that other people can understand. And that's just practice. So I think it would be more useful to study some specific science that you can't just learn through practice, like astronomy or biology or computer science or physics or whatever, because the concepts that are part of that process require that specialized knowledge to be able to do. And I'm limited all the time by what I can and can't report very well, by my own knowledge. My knowledge is very broad. I can explain lots and lots of stuff, but if I was going to have a conversation with someone like Scott Manley about rocket science, he would just do circles around me. Or if I was going to talk to Matt O'Dowd from PBS Spacetime about cosmology, again, you'd be doing circles around me because I just don't have that depth of knowledge. And so I think if you want to study, pick a subject that you're really interested in, study that at university so that you can become very knowledgeable about it, and then be able to communicate that out to a wider audience. And a lot of universities offer communications courses, but just at the end of the day, just a lot of writing. Write. Or other kinds of journalism that you like to do. Ted Spears, do you have any thoughts about Robin Hanson's grabby aliens model? Yeah, so I've interviewed Robin Hanson here on the channel about grabby aliens, and we talked about it for quite a while. So I didn't really understand it until I talked to him, although I sort of intuitively understood and have been thinking about a lot of the same problems. With the grabby aliens model, what Hanson is saying is that if an intelligent civilization gets going, then that civilization is going to go out into its surrounding space very rapidly, approaching the speed of light. Imagine self-replicating robot probes that are going to a new star system. They are crunching down the star system. They're sending out more robot probes. They're going to the next star system. They're crunching more, material down. They're building more robot probes. They're just going in this ever-expanding sphere of exploration. And then they are turning whatever it is they find into the most practical purpose for their needs. So they are covering up stars in Dyson spheres, or maybe they're dismantling stars and turning them into small red dwarfs, which is more efficient for their uses. Or maybe they're rearranging the stars into positions that are more economical for them to be able to send spacecraft back and forth. That an advanced enough civilization should be interacting with the universe as its environment in the same way that humanity interacts with planet Earth, right? You can tell that humans are here because you can see our cities. You can definitely see them at night. And so the assumption is that if there was an advanced enough civilization, they would be having an impact on the cosmos that we would be able to see. And yet, when we look out into the universe in all directions, we just see wilderness. We don't see a rapidly expanding civilization. We don't see multiple rapidly expanding civilizations in all directions with their borders bumping up against each other. And so Robin says, well, that's useful. That tells us something about where we are in the universe. The fact that we don't see advanced civilizations allows us to try and figure out how many civilizations there are out there and how far away it is to the closest one, because we wouldn't see one of these civilizations until they swept past us at close to the speed of light with their front of von Neumann probes dismantling star systems as they go. And so I like that idea. I mean, I don't like that. I mean, I don't like the idea of a expanding swarm of von Neumann probes dismantling star systems as they sweep out in all directions. I don't like that idea at all. But like philosophically, that idea does resonate with me. When I have conversations with people about the Fermi paradox, like, I know what their answers are going to be. And you're thinking them right now, right here, right? No, we've just barely started to look for alien civilizations. Oh, space is really big and nobody can ever go anywhere. Why would they choose to go out into the universe when they might just want to stay home, and so on and so forth, right? There are all these, like, everything that you can think of has been proposed, and there are answers to every single one of those things. And so I always say that I think we're alone in the universe. Robin disagrees with me on that one, but he just thinks that they're far enough away that we haven't encountered them yet, but they're coming in our direction from all directions at close to the speed of light, and it's just a matter of time before they get here. I hope not, because that would be scary. There's a great description of the grabby aliens from Rational Animations, which is such a good channel. Like, if you like Kurzgesagt's animations for stuff about space and stuff, I highly recommend you go and check out Rational Animations. They're really good. So they've got a great explanation on the grabby aliens model, and it's great. I think it's really clever. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version? It's an hour more. You can sign up for a special patron-only podcast feed and get the overtime segments, as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who has already subscribed, and welcome to our recent newcomers: Eric Snow, Seals McBeal, Terry Robinson, Frank Stewart, Peter G. Haltson, Andrew Loss, Sander Holbrand, P. Sprout, Sri Ram, Doreen B., Reed Robinson, and Bob Cook. Join the club at patreon.com/universetoday. K-Swiss. With all these companies sending up all these tiny data satellites, well, they have to stay at different altitudes. How do they stay safe? Nobody knows. So this is going to be a big problem, which is that although space is really big, it's right there in the name, the space in low Earth orbit where these various communication satellites are going is becoming more and more congested over time. And it's not just the satellites themselves, it's all of the defunct, the dead satellites that are there that are no longer able to reorient themselves. It's all of the space junk. It's estimated that there are millions of pieces of space debris that are like a millimeter or larger orbiting the Earth at various altitudes. And a 1 millimeter chunk of metal moving at 28,000 kilometers per hour hitting a spacecraft can cause damage. And then it could cause damage to that spacecraft. That spacecraft could shut down. It could get hit by other debris. It could break up into more debris. So there's a very large concern that over time we will have more and more space debris, and any satellites that are in orbit around the Earth at various altitudes will be at greater and greater risk. And eventually it will become just not feasible to launch satellites because there's so much buzzing metal around the Earth that anything you try to launch into that altitude is just going to get torn apart and add to the problem. And so this is known as the Kessler syndrome. Like, what's the solution? The solution is to negotiate. For the lowest orbits, the stuff that's, say, around the altitude of the International Space Station and below, stuff there deorbits relatively quickly. There's still atmosphere there. And so these bits and pieces of debris get slowed down by the atmosphere, they re-enter, they burn up, and so it's sort of a self-cleaning mechanism. But at higher altitudes, this stuff will last for decades, and eventually it'll last for centuries, and then eventually it'll last for millennia, and then eventually it'll last effectively forever. And so those higher orbits, even though they're bigger, it would be such a bad thing to have tons and tons of satellites tearing themselves apart in that orbit, because there's no cleaning it up ever. And it's never going to get cleaned up by the Earth's atmosphere. You're done. You're stuck with it. You've got this orbit that is filled with metal, that is, buzzing around. And if you try to put anything there for any amount of time, then you've got a problem. Now, we'll probably never be cut off from space because, if you go quickly through these various orbits, the chance of you interacting with anything is incredibly low. But it's really, if you're going to try to stay there. So space is really big, and the orbit around Earth, there's tons and tons of space. You could, like, when we think about how aircraft work, how shipping lanes work, there's a lane that you take through the Pacific Ocean or the Atlantic Ocean when you're going to go from North America to Europe. And then you take a different lane to go from Europe to North America. And these lanes are separated by large distances, and all the boats are going in one direction, all the boats are going in the other direction. Same thing with airplanes. Airplanes follow various tracks that are pre-planned in advance, and they stay in corridors that are away from each other. And so if someone, if some international community was willing to just sit down and go, okay, here's one ring where all the satellites go together in this direction, and then here's this other ring where all the satellites go, and then and because you can work in 3 dimensions, you can have them be separated, you can have them move in ways that they'll never interact with each other. And it would be incredibly safe compared to what we've got right now. Like there's no rules right now. Right now, you just launch wherever you want to go, do whatever you want. Countries don't talk about it. And we know that this is unsustainable. Like, the amount of satellites that you could launch is like a few every year to make low Earth orbit be sustainable. And we're way beyond that. So, yeah, somebody's got to talk and figure this out, or the problem is just going to get worse and worse and worse. Tommy 36. Why is the stellar mass black hole merger theory more popular than the direct collapse theory for supermassive black hole formation? The only way that we know to get a black hole is to have an implosion of a star. That it's not enough to just have a lot of material collected into a small area and then have that area collapse under its own gravity. That's how you get a star. And the problem is that there is a limit to the size of the largest star. So beyond about 100 times the mass of the sun, as material is accreting down onto the star is getting so hot, it's so large, it's getting these outflowing winds and jets that are blowing away from the star, and then no more infalling material can fall down onto the star. And so that's why, like, the limits, the largest stars that we've ever found are like 150 times the mass of the sun. And even that is sort of up for grabs. And when a star that is, say, 100 times the mass of the sun detonates as a supernova, it doesn't even create a black hole. They're called pair instability explosions. And so there's no remnant left behind. And so you need the right size star to be able to get a black hole. And it is, you're going to end up with a black hole that is some number of times the mass of the sun. And then you're going to need to have those two stars find each other, and they're going to need to merge into a larger black hole. And then those are going to need to merge into others to merge into a bigger black hole, and so on and so forth. The direct collapse method, where you just have an enormous amount of material, and then somehow that material can come together and form an object that has so much gravity that it doesn't even turn into a star. It just turns directly into a black hole. This is absolutely a mainstream concept. But the question is, we see stars today that refuse to get bigger than 100, 150 times the mass of the sun. And so how could you get one that is 1 million times the mass of the sun, 4 million times the mass of the sun, to get that supermassive black hole? And so the one possibility is that there's something different about primordial hydrogen and helium left over from the Big Bang, that the stars today, they're polluted with other heavier elements like oxygen or carbon, and somehow that pollution is the cause for stars not being able to form to become supermassive. And maybe when you just have pure hydrogen and helium, you can get these supermassive stars. But other people don't think that. They think that, yeah, you would get larger stars, but they would also live very short lives. They would explode as supernova, and they just wouldn't get 1 million times the mass of the sun. But the sort of interesting theory, and there's some evidence for this now, thanks to James Webb, is that, there needs to be some mechanism that is preventing the outflow winds from stopping from the star being able to halt its growth. And that there could be some kind of process in the early universe with these primordial stars that they're able to prevent the outflows. And so they do just keep accreting mass until they become a supermassive black hole. And having the direct collapse of supermassive black holes would solve so many problems, right? It would explain how you have supermassive black holes at the hearts of almost every galaxy out there. It could explain why we're seeing such big galaxies early on in these James Webb observations. Like, there's a lot of stuff that the direct collapse solution to the problem solves. But it's just, we don't see stars doing it today. Why would stars have done it in the past? This is the question. And that's why astronomers are skeptical that direct collapse is the answer. But if one day someone sees one in action, we see a direct collapse black hole starting to come together, and they understand the mechanism that stops it from halting its growth, then that will be the accepted scientific consensus. Don Campbell, when do you think we'll become a Kardashev Type I civilization? So Kardashev civilizations, Type 1, Type 1, Type 1, Type 2, Type 3. Type 1 is where a civilization is using up all of the energy that falls on its planet. So you imagine like all of the sunlight falling on Earth. If we were able to cover Earth in solar panels, we would be a Kardashev Type I civilization. Now, obviously, that's not what you'll do. You'll have all kinds of space stations and solar power generating stations. You'll have O'Neill cylinders and all kinds of stuff orbiting around the Earth. But the crazy part is that it won't take us that long. If you just take the growth of humanity, you go back 10,000 years, you can chart on a logarithmic graph, on an exponential graph, how we are increasing our energy usage over time. And you can then take that line and then you can chart it into the future. You can say, okay, in about 200 years or so, if our energy usage continues, then we will reach Kardashev 1 level scale. In other words, all of humanity will be using the equivalent of all of the sunlight that falls on planet Earth. And I know that sounds crazy, right? That sounds bonkers. That's too much energy. What are we going to do with all that energy? So we don't know, right? That exponential curves sometimes turn into S curves. So they rise at an exponential rate, and then they slow down, and then they flatten off. And so we could be at the turning point of the S curve, and now our energy use is going to go down, and then it's going to flatten out, and then maybe it's even just going to drop. Or maybe, like all of human history, we will come up with new ways to use energy into the future. And we'll just keep doing that forever. And so if we reach that type 1 civilization in a couple of 100 years, then your question might be like, when are we going to hit a type 2 civilization? When are we going to build a Dyson sphere and use all of the energy that is being expended by our sun? And so you can just take that same energy growth and you can just keep charting it forward. And the point that you get to all of the energy being put out by the sun is just a couple of thousand years from now, which is not that long, right? Like when you think about all of human history, a couple thousand years ago, humans were roughly the same as we are today, with less technology, but a couple thousand years from now, using up all of the power. So again, at some point, it's going to turn into an S curve, and then our power use is going to decline, and we'll live in sort of perfect sustainability with our planet. Or maybe we will just keep going and figure out new ways. Maybe we'll, come up with more powerful computers. Who knows? And then the next question is, well, when are we going to create a Kardashev III civilization where we're using up all of the energy of our entire galaxy? And the problem there actually is that it's the speed of light is the challenge that it's going to take you years, thousands of years. It would take you, even moving at the speed of light, it would take you about, say, 100,000 years to reach every star system in the Milky Way. And so at the bare minimum, like if all of the stars in the Milky Way were compacted really close together, it would only take a couple of thousand years after that to use up all those stars. But because we have to travel to them all, you pretty much then have to make the speed of light be your limiting factor. So a couple 100,000 years from now, we, or our robot overlords, come on, let's be honest, will be a type 3 civilization unless the power curve flattens out. And this is back to that comment that we had earlier about that Robin Hanson about the grabby aliens, that if it's only going to take us a couple 100,000 years to become a type 3 civilization, why don't we see the type 3 civilizations out there in the universe? We just don't. It's a paradox. Jim Jeff, I keep hearing the size of the universe was at one time spherical, a basketball, for instance. If you use that, how could it possibly be flat? Did it flatten out as it expanded? All right, so there's a bunch of concepts in there that I'm going to have to dismantle one by one. So the first thing is that you hear that the shape of the universe was one time spherical, and then a basketball, for instance. So I think what you're conflating here is that at one point in the past, the observable universe, this sphere of universe that is centered on you, Jim Jeff, was once the size of a basketball. And that is theoretically correct, according to our current models of the expansion of the universe, that this thing that is now 46.5 billion years to your right, and this thing that is 46.5 billion light years to your left were once this far apart. That is true. And that is mind-blowing, right? And that over the 13.8 billion years, you've had all this expansion and these things have moved away and away and away. But that is just your observable universe. And so on Vancouver Island in Canada, I see a different observable universe. I see a slightly different sphere than what you see. And so the basketball-sized universe that I saw at the beginning of the universe was a slightly different sphere than the one that you see. And that means that there was actually more universe. Our universes were overlapping. And yet, we sort of saw different universes. And that's because there's just more universe outside of what you could see and what I could see back at the beginning of the universe, if we could, which we didn't, unless we're time travelers, which we're not. It's thought that, in fact, the actual universe is hundreds, maybe thousands of times bigger, like volume-wise, than the universe that we can see today. And it could very well be infinite. And so that is like a separate conversation from the flatness of the universe. And when astronomers talk about the flatness of the universe, all they're really talking about is, do parallel lines stay parallel in the universe the way parallel lines don't remain parallel on the surface of the Earth? So that's maybe that's a question for a different time. Perceive Chiasa. What does it mean that some planets have no surface? Well, think about the giant planets here in the solar system, like Jupiter and Saturn and Uranus and Neptune. If you could visit the surface of Jupiter, which is considered a gas giant, and it's made mostly of hydrogen and helium, the same stuff that you would find on the surface of the sun, and you were to stand on the surface of Jupiter, you would fall, because, even though, it's cloud tops and you would be falling into the clouds, and then you would fall and you'd fall and you'd fall. And then the pressure and the temperature around you would increase, because you've got all of this hydrogen and helium that is under intense gravitational pull from the planet. And so it would become more and more soupy, even though it's still just hydrogen and helium. And eventually it would be incredibly hot, like you would die because it's so hot. And it would just keep getting hotter and hotter and hotter. That the center of Jupiter is tens of thousands of Kelvin. I forget, it's like 50,000 Kelvin. And like that's hotter than the surface of the sun. Like many times hotter. That's hotter than the surface of Rigel that we talked about earlier on. That's only merely 12,000 Kelvin. So that is incredibly hot. And that's just because Jupiter has an enormous amount of gravity and temperature and pressure, and things just heat up and heat up inside as you get closer and closer to the center. And if you made Jupiter bigger, then it would have more mass, and then it would be able to have an even hotter core. And at a certain point, that core would be so dense and so hot that it would start to ignite fusion in the middle of that planet. And now you would have a star. So, Jupiter doesn't have any surface that you could walk on. But, if you tried, you would just fall into the cloud tops. But you would find very quickly that actually things become very hot and dense inside the planet. And same thing goes for Saturn. Same thing goes for Uranus. Same thing goes for Neptune. Pet pleased. Which costs more, preserving Earth's environment or exploring space for a new habitat? Consider factors like funding sources, project scopes, and long-term objectives. Preserving Earth's environment is the best investment we could possibly make for the long-term sustainability of the human existence, not to mention all of the biodiversity, all of the animals, and so on. Like it's really hard to get across to people how awful everywhere but Earth is. Like if you take Mars, which is like the most habitable place in the solar system, still there's almost no atmosphere on the surface. The gravity is a fraction of what you have on Earth gravity. It is bombarded by radiation from space. There's no water on the surface. There's no air you can breathe. There's very difficult to access resources that you could use. It's a terrible, terrible place to live. And then a place like Antarctica is so much more habitable than Mars. And so, I don't even think it makes sense. I think that if people make this straw man argument on the internet where they say, well, if people want to go to space, that means that they don't want to preserve the Earth. But it's kind of like saying, if you want to climb a mountain, it means that you don't want to clean your house. You're not climbing the mountain so that you can get away from your house. You're climbing the mountain to climb the mountain. And if you left the dishes undone, when you get back to your house, you're going to have to do the dishes, because you're not going to live on the mountain. You're not going to live on Mount Everest. Mount Everest is trying to kill you. That you get beyond a certain point at altitude on Mount Everest and you're in the death zone and you're living on borrowed time, and all you've got is the food that you brought with you and the supplies, and you're going to be, you're going to run out of gas to heat your food up, and you're going to freeze to death. And so you got to get to the top of that mountain, you got to get home. And once you're home and you've got nice comfortable temperature and you've got food in your fridge and you got your friends around and you can go for walks in the park and you take your dog and it's all nice, right? You're going to do the dishes in your house because that's where you live. And so to take that analogy, to torch that analogy, right? That there is just like, there's no connection between those things. That us trying to explore a place like Mars doesn't mean that we're going to try, if we can't sustain our environment here on Earth, then we're not going to be able to do things like go and explore Mars. And I guess, if you don't wash your dishes, then you won't be able to climb Mount Everest. I don't know. All right, those are all the questions that we had this week. Thank you, everyone who asked the questions in the YouTube comments, and thanks everyone who showed up for the live show, which we do every Monday at 5 p.m. Pacific time, right here on the channel. I'm going to put a reminder on the channel so that you can see when the next one is going to happen, and I'm sure you can set a reminder so that you'll receive an email. I promise YouTube will tell you when the next show is going to be. Now, I'm going to continue promoting smaller YouTube channels, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew M. Gross, Antonio Lofilara, David Gilton, Dougie Stewart, Dustin Cable, George, Jeremy Mattern, Jordan Young, Josh Schultz, Mark A. Mandel, Mark Anstis, Paul Rohrbach, Stephen Krasaki, Stephen Filer Munley, and Vlad Shiplin, who support us at the Master of the Universe level, and all of our other patrons. All your support means the universe to us. All right, so I'm going to continue my campaign of trying to bring attention to smaller YouTubers. And so this week, I want to suggest you check out the Ad Astra Space channel, which is hosted by Swapna Krishna. And she is a space journalist who has worked for a lot of the names that you've heard before, Space.com, Wired. She hasn't written for Universe Today yet, but she does a great job. Her channel is terrific, and she's been doing a lot of coverage, most recently just on the Odysseus lander. And while I did one episode, she's done a whole bunch, sort of covering each point of it. And so, a really great coverage of space exploration news. And you can see she's got chops, and yet for some reason she doesn't have a lot of followers. So, it's just a matter of time. You'll remember when you're one of the first people to subscribe to her channel. So definitely check out Ad Astra Space. And please keep sending me the names of YouTubers who have less than 10,000 subscribers, people who are new to the scene or just for some reason aren't getting a following. I want to try and drive as many new subscribers as I can to those people. All right, we'll see you next week.